So now let us start the derivation of RDT. See, we already done all the background work. What are the background works? We know that why we need RTT. RTT is the link of physical, physical laws of system with physical laws of, like I am linking the physical laws of this system with control volume, because there is no physical law which is directly defined for control volume. Okay. And we understood how to find out net rate of efflux or net rate of outflow of some particular property over the control surface. We found out the formula for it. Now we will see this. Let us consider there is a flow which is happening. Okay, you consider it like this. Okay, a flow which is happening at some particular time t. Okay, at some particular time t, I am defining a system. Okay, I am defining my system as this blue color line. Okay, so whatever the molecule which is present inside, okay, whatever the molecules which is present inside this blue color line, it's constitute my system. Okay, and at the same time t, okay, at the same time t, my system is exactly what I could say superimposed on the control volume. You can imagine it like this. This is my control volume. What will happen to my system? System will be continuously flowing. Wherever it goes, it will be continuously flowing. So at time t, okay, at time t, my system and control volume are getting superimposed. So this blue color, like it's actually a cylinder. Okay, so it's actually a cylinder. This blue color, what I could say, the particular area represent my system and also control volume at time t. Okay, at time t. And moreover, this control volume I can refer like this. Okay, control volume will be, this blue color line will be my control volume at any time, because if time continuously varies also, my control volume is not going to vary. It is fixed at one position. It's fixed at one position. It's fixed with respect to that particular space. I'm not varying my control volume, but system will vary. Bunch of molecules will travel from one place, it will go to another place, it will be traveling and it will be reaching some other places. So system will vary, but control volume position is fixed for all the times. Okay, for all the time the position of control volume is fixed. Now let us consider there was some small increase in time, very small increase in time. So where will be my system at time t plus delta t? So if time increases by a small value, okay, if time increases by a small value, how will be my system looks? So flow is happening in this direction, right? Actually my system will be continuously flowing. So after a small time delta t, let us imagine my system has moved like this. Okay, so this is my new position of system. Okay, so this red color dotted line representing my what is that, system at time t plus delta t. Okay, so this is system at t and control volume is superimposed, or it is merging with system, okay, at time t, but control volume will remain same for all the time. It's something like this. Control volume is fixed, system is moving, and system is exactly merging with control volume at time t. And when time increases by delta t amount, system is further moving, but control volume will still remain at the same place. That's what. Okay, right. So this is system at t plus delta t. Now at a time t, okay, so we can take like this. We will take this section as 1. Okay, only this part. Okay, only this part as 1, this part as 2. So at time t, my system and control volume both are present at part 1 and part 2. Okay, at time t plus delta t, listen carefully. At time t plus delta t, where is my control volume? At time t plus delta t, where is my control volume? It is still 1 and 2 only, because my control volume is not changing, right? Whatever may be the time, my control volume is still 1 and 2 only, it is not changing. Okay, but my system at time t plus delta t is 2 plus 3. Is it clear? So now this understanding is going to helpful when we are deriving the relation. Okay, let us start Before going into the derivation, you need to know one basic differential calculus. Suppose if there was a function f, and if I want to differentiate with something, we will take it with respect to x. Okay, if I want to differentiate with respect to x. So how you will write basic differentiation formula? How you will write? Simple, limit delta x tending to 0, f of x plus delta x minus f of x by delta x. Sometimes instead of delta x, we will use h tending to 0, f of x plus h minus f of x by h. You have to recollect this from your basic differential calculus. So wherever you attend differential calculus, I think the second lecture or something, they will give you this. When they are defining differentiability, continuity and differentiability, after limits, they will be giving you this definition. Okay, so this is the basic definition of differentiation. Now, we already taken a property called as B, right? Capital B, it's an extensive property. If I want to find out what is the rate of change of, understand carefully, rate of change of that particular property B in the system. I'm not finding out for control volume, for the system. So rate of change of that particular property B with respect to that particular property B with respect to system. And one small change I need to do here. If you take system will be continuously moving, right? So the properties, whatever the extensive property which I am taking, that will continuously vary except mass. Okay, so mass is not going to vary, but I'm just giving you some in a general case. Okay, in a general case. Later when I do mass conservation, you will understand that mass is not going to vary. Let it be now. So the property is going to vary with respect to space and also with respect to time. That means this B, okay, will be function of x, y, z and also time. So it's not only function of time, it's a function of space and time. If that is the case, then how to specify rate of change of some particular property? I already given this when I am discussing, I think, acceleration in fluid kinematics. What is that? Material derivative. I should not use normal derivative because B is not a function of only time. B is a function, it can be function of space, it can be function of time also. Right, so it's a combination. It's a combination of function of both space and time. So I should not use this small d. I should use capital D. So let me just change it. It's going to be d b by d t. And what it is indicating? It's a material derivative, and I already given this. And what is this material derivative indicating? Rate of change of this particular property B. And now I am finding out for system. Okay. Okay. From the basic definition I can write limit, and here it's not with respect to x, I am finding with respect to t. So delta t tending to 0. From where to where? From where to where? From where to where? Actually it is varying. Initially system I am taking at time t. Later I am taking system at time t plus delta t. So numerator will be something like b at time t plus delta t minus b at time t, okay, by delta t, right? F of x plus delta x minus f of x by delta x. Similarly, b at t plus delta t. Okay, what is property b at t plus delta t minus property b at t divided by delta t, where delta t is tending towards 0. Okay. Now, t plus delta t means what are all the components we are having? At t plus delta t, my system is present at 2 and 3, right? My system at t plus delta t means what? 2 and 3, right? So I will divide it and I will write something like this: limit delta t tending to 0. I will write it like b2 plus b3 at t plus delta t minus, what about at time t? At time t, okay, at time t, my system was at, I am doing it for my system only. So my system at time t was at 1 and 2, okay. At time t, my system was at 1 and 2, okay, very good. Let me use the space here. So b1 plus b2 at time t, the whole divided by delta t, okay. So dB by dt of system will be equal to, so what happens now? I will do some small rearrangements. Okay, so what I will do, limit delta t tending to 0. Let me first take this t plus delta t inside. Okay, so first I will write it like this, b2 at t plus delta t plus b3 at t plus delta t minus b1 at t minus b2 at t by delta t. Okay, now listen, I will do one small thing. I will add one quantity and I will subtract one quantity. Let me erase it. So now this is the final equation which we got. Okay, now listen carefully. What I am suggesting you now, if you are writing parallelly when I am teaching, please stop. Okay, don't write it, because this step is something which is which you need to understand properly. Okay, right, listen. What I am doing now, I am going to add b1 at t plus delta t. Okay, at time t plus delta t, I am adding b1. Okay, that is this part property at time t plus delta t, and I am subtracting b1 at time t plus delta t. Okay, why I am adding and subtracting? Because if I add and subtract, anyways it will cancel, right? So the equation is not going to vary. But I am adding and subtracting for simplifying it further. You will understand it why. Listen carefully. If I add b1 at t plus delta t, okay, so I will take this, I am keeping it here, b1 t plus delta t, and I am taking this and I am keeping it here. Okay, so this is gone. Let me show you. This 2 has been taken. Okay, and I placed it here, and I am taking this 2. Okay, b1 at t and b2 at t. Okay, b1 at t and b2 at t. So the remaining, what are the remaining things? b3 at t plus delta t and b1 at t plus delta t, but this has to be subtracted. Okay, so b3 at t plus delta t minus b1 at t plus delta t. A simple step, some rearrangements. Okay, now listen. Okay, what is this b1 plus b2? b1 plus b2 is nothing but control volume, right? Control volume. At what time? At t plus delta t time. Okay, at t plus delta t time. Now this I could take it commonly and I can write it like this. Can I write like this? Two minuses are there, I taken minus commonly. Okay, so I will specify with another color so that it won't confuse you. So this is a control volume, b1 plus b2 at time t plus delta t, again b1 plus b2 at time t. So the difference of this two, okay, by delta t. Listen carefully. b1 plus b2, it's my control volume at time t plus delta t. Similarly, b1 plus b2 at time t. Okay, I am finding the difference of that two and I am dividing by delta t and I am applying limit delta t tending to 0. So what is this total? What is this total term indicating? By basic of differentiation. Limit delta t tending to, just now I given the equation, limit delta x tending to 0, f of x plus delta x minus f of x by delta x. So limit delta t tending to 0, control volume condition of B, okay, control volume condition of B at t plus delta t time. Okay, because control volume will always remain as 1 and 2 only. Control volume is never varying. Okay, so B1 plus B2 control volume condition at t plus delta t minus b1 plus b2 control volume condition at time t. Okay, I'm finding the difference of this two, dividing with delta t, and I'm applying delta t, limit delta t tending to 0. What is this indicating? Come on, yes. See, basic definition of differentiation only. df by dx will be equal to limit delta x tending to 0, f of x plus delta x minus f of x by delta x. Similarly, here it is d property b, okay, property b by dt, okay, d property b by dt, and this is taken for control volume only. Why control volume only? Because 1 and 2 combinedly is my control volume. 1 and 2 combinedly is my control volume. This is control volume condition at t plus delta t. This is control volume condition as at t, dividing with delta t, and I am applying limit delta t tending to 0. Same as the basic definition of differentiation, right? So if you understood this point, then we almost done. Okay, So this is indicating dB by dt of control volume. 1 point. If you understood this, rate of change of the property B in the control volume. Why I am taking in the control volume? Because this is control volume condition, this is control volume condition, difference of that by delta t, and I am applying limit delta t tending to 0. So this corresponds to dB by dt of control volume. But I won't use D. Why? In control volume, I said at the beginning itself, control volume's position is fixed always. Control volume's position is fixed always. Position is constant. So if suppose the property B is function of x, y, z and time, I am fixing my position as constant, which means x, y, z is constant. What type of derivative it is? It's a partial differentiation, right? So this is dou B by dou t. Why I am using partial differentiation? Understand it properly. For control volume, position is fixed. Position is never going to vary. So if I differentiate some function by fixing the position as constant, very clear cut idea. If I differentiate some function by fixing the position as constant, then the differentiation is called as partial differentiation. So this is indicating rate of change of property B, okay, in the control volume. Since in the control volume position is fixed, I am using partial. Position is fixed means position is constant, so I am using partial differentiation. That's it. Well and good. Now what is that? You understood this, then what about that? This is something which is very, very easy. What does that means? Listen, both B3 and B1, okay, both B3 and B1 I am taking at what time? Listen carefully, at time t plus delta t only, okay, at time t plus delta t only. Now at time t plus delta t, with respect to control volume, you speak with respect to control volume. With respect to control volume, what is this B3? Understand properly. At time t plus delta t, okay, B3 is nothing but the quantity which has come out of control volume, right? Listen carefully, I will explain properly. See, this is my control volume, okay. At time t, both system and control volume are merging, are coinciding. At time t plus delta t, this much quantity, okay, this much quantity left my system, it's leaving my system at time t plus delta t. At time t, there is no issues, both 1 and 2 system and control volume is merging. But at time t plus delta t, this much amount of quantity left my system, okay, it is leaving my system, okay, very good. Now, what is this indicating? At time t plus delta t B1, at time t plus delta t, this much left the system, sorry, left my control volume, this much added to control volume. This is net outflow, sorry, this is outflow, this is inflow. Bit, what I could say, it's not that much straightforward thing to understand, but if you get the logic, that's it. The concept is almost done. We can finish the remaining things, remaining procedure, and we can proceed to Navier Stokes. Okay. Let me repeat it. At particular time t, both system and control volume is merging. Control volume will remain same only throughout the time, it's not going to vary. But molecules will enter, molecules will leave. Some molecules with some property will enter and some property will leave. Now at time t, my system and control volume are same. So all the molecules of system is present inside the control volume. Okay, all the molecules of my system is present inside the control volume. At time t plus delta t, this much amount of molecules, okay, this much amount of molecules left my control volume, right? It is leaving, it is coming out of control volume. This is outflow, outflow of the particle, sorry, outflow of the property B, capital B. At same time t plus delta t, initially at time t 1 plus 2 was there, which is merging with system. Now at time t plus delta t, when this system is moving outside, okay, when this system is moving outside, when this much amount of quantity moved outside, this much amount of new quantity entered inside. So this is outflow of the property B, this is inflow of the property B. And what you can say about this? Listen, change of, or you could say that net outflow minus net inflow, outflow minus inflow of the property B, outflow and inflow of the property B. This is outflow, this is inflow at time t plus delta t of the property B. I am finding it with respect to time. So what it is indicating? What it is indicating? It's indicating, I will just write it like this, okay? B dot net output, which is equal to summation of control surface small b into rho v vector dot a vector. I derived this, right? So this is nothing but net rate of outflow of B. This is outflow minus inflow, and I am calculating with respect to time. Okay, so net rate of net rate of outflow of the property B over the control surface. Of course, this much. Okay, this much is leaving the control surface, right? This much entered the control surface. This much quantity left the control surface. This much quantity entered the control surface at time t plus delta t. Okay, simple now. We almost done. So what is my final thing? dB by dt of system, okay, is equal to, this is dou by dou t. How can I write this B? B is the property, right? Some extensive property. Just say me that, can I write like this? Triple integration over control volume. I am finding it for control volume only, right? I am finding it for control volume only. So triple integration of control volume B into rho dV. Listen carefully. B into rho dV. First of all, what is this rho dV? dV is small volume which I am taking. For example, you can consider that I am taking a small volume. Okay, this is dV. Okay, small volume inside my control volume. If I multiply with density rho, I will get mass of this small volume. Okay, if I multiply with density rho, I will get mass of this small volume. And if I multiply with intensive property, this small b is specific, right? Specific means capital B by E. We already know, I already given you capital B by M, right? So small b is capital B by M. So if I multiply that small b with mass, okay, with mass of this small volume, I will get the property B, okay, property B of this small volume only. Now if I triple integrate it, that is if I find volume integration, I will get total property. So simply B, or I will write like this, dB is equal to B into rho dV. I hope that you could understand this. Okay, what is this dB indicating? dB indicating small property, or else I will repeat it again. dV is nothing but this small volume. If I multiply with the density, I will get small mass. If I multiply with the specific property, I will get the property B corresponding to this small volume. Okay, property B corresponding to this small volume. If I want to find out over the complete control volume, then I need to volume integrate, because it is dV dash, right? Here V dash indicating volume. So I need to apply volume integration. Okay, so that's what I'm doing here. So instead of B, I'm taking volume integration of that. Okay, plus this is summation over control surface rho B. I will take like B rho. Okay, so I think that will be better. Yeah, B rho V vector dot A vector, or in other sense, I need to use summation if the velocity profile was uniform. If the velocity profile was non-uniform, then dB by dt of my system will be equal to dou by dou t of control volume B into rho into dV plus summation of, I'm very sorry, double integration over control surface, okay, double integration over control surface B rho V vector dot dA vector. This is my RTT. Relating system with control volume and control surfaces. So this is the final equation which we got, and what it is actually indicating. You could see here the time rate of change of the property B in the system. Okay, so time rate of change of the property B in the system is equal to, so this is specified with dB by dt for the system. It's equal to time rate of change of the property B again. So this is time rate only, right? Why I am using partial derivative? Because in control volume space is fixed. So time rate of change of the property B in the control volume. So this is our property B. If I find out volume integral of B rho into dV. So if I use this symbol, it indicates volume. Okay, it indicates volume, and plus it is net outflow rate, or in other words net efflux rate, okay, of the property B over the control surface CS. So RTT, Reynolds Transport Theorem, is linking systems equation with control volumes equation. And now let us start doing this. Okay, so what I will be doing from the next video, simple. First, I will take B is m. Okay, that is the property, extensive property B as mass. Okay. Second, I will take that property as linear momentum. So I will get linear momentum conservation equation, such as I could convert it from the linear momentum conservation equation of system will be converted into control volume. And in the next, I will take B as angular momentum. So these two are momentum conservation equations, okay. And finally, for B will be taken as energy, okay. So this is mass. So these are the four things. So I will be getting energy equation. So these two are momentum equation, energy equation, and this will be my mass conservation equation. So this is the next four videos all about. So you have to remember this particular formula, okay. And now I'm going to use this formula and I'm going to substitute all these things. So now let us start with conservation of mass. So conservation of mass means what? First, what I will be doing, I will be taking B as m, okay, so which is nothing but mass. So B is equal to m, then what will be small b? Small b is nothing but capital B by mass, right? So which is nothing but m by m, which is equal to 1. So simply in your RTT, Reynolds Transport Theorem, wherever capital B is there, replace it with mass, and wherever small b is there, replace it with 1. So if I do that, what will happen to left hand side? It's going to be dm by dt, and this is for system, okay. So time rate of change of mass in the system. So that's going to be equal to dou by dou t triple integration of control volume. Small b is going to become 1, right? So 1 into rho dv, okay, plus again double integration of control surface. Again small b is going to be 1. So rho into v vector into dA vector. In sometimes this can also be written as, I already given this, n cap into dA, okay. Sometimes this can also be written like this, okay. It depends on the book, depends on the books, okay. So we are going to follow this, okay. Now so anyways I can just take this 1, right, because I'm replacing B with 1, okay. So just think about this term dm by dt of system. System will have some fixed mass, okay, and that fixed mass will remain same throughout. If I am fixing some bulk of molecules, and I am just fixing that bulk of molecules and I am following it everywhere wherever it goes. So the molecules or the mass or the matter of the system, okay, the quantity, or I could say that physical identity of the system is not varying. It is remaining constant, right, every time. If it is at a position, at this position or this position or that position or this position, wherever it flows, identity, physical identity or the mass of the system remains constant. That's why it is also known as fixed mass. Since it is fixed mass, for a system, change in mass with respect to time will be what? It's going to be 0. This is pretty obvious, everyone knows. Okay, mass has to remain constant. If you take a container, if you fill something and if you move the container wherever you want also, the mass which is inside the container will remain same only until you pour it somewhere. If you are not pouring it out, the container mass will be same everywhere. So that is what like system also. Imagine a what I could say, hypothetical container where you are filling a mass and it is moving everywhere. Okay, it is moving everywhere. So obviously this is going to become 0. Right, so change in mass with respect to time will be 0 for a system. Now, this is one thing, so I can write it. Let me write this to equation left side. Okay, so dou by dou t triple integral of control volume rho d dash v plus double integral of this rho v vector dA vector. Okay, very good. So that's going to be equal to 0. Okay, so this is our mass conservation equation for my control volume and control surface, or simply mass conservation equation of a control volume, because control surface is the boundary of control volume. Now still I can modify this. Okay, so if possible you remember this, or even this also it is not required. If you remember Reynolds Transport Theorem, and wherever b is there replace with small m, wherever small b is there replace with 1, you will end up in this equation. Okay, now further simplification, what I could do. So first time I am including one assumption. Until now I didn't assume anything, right? So the first assumption which I am going to include is steady state. Okay, steady state. If I assume steady state or a steady flow, what will happen? What will happen to this term? This is time rate, right? Time rate or time rate of change of this particular quantity. So this is what actually rho into dV. Rho into dV is the small mass. Density into small volume is the small mass. And if I volume integrate it over the control volume, I will get the total mass. So if I take it as steady state, then inside my control volume, mass will remain constant. This concept I already explained to you when I was discussing steady flow energy, steady state energy equation in thermodynamics itself. So mass inside the control volume will remain constant if it is a steady state, which means whatever it is entering. Okay, if I take a control volume, okay, if I take a control volume like this, whatever mass it is entering, same mass only it will leave, which implies mi dot is equal to me dot. So which clearly indicates that dou by dou t of triple integration of control volume rho into dV. Okay, this triple integration of control volume rho into dV is nothing but mass. So it's like time rate change of the property. In this case, the property is mass. So this is going to become 0. Okay, so this term will be 0. So if this term becomes 0, now what is my mass conservation equation? Very simple. This, right? Only this is remaining, because this becomes 0, right? It becomes 0. So only this is remaining. Okay, only this is remaining. So what I will get? Double integration of control surface, yeah, which is equal to 0. So I am getting this equation after assuming that it is steady state. Only one assumption. If I include the second assumption, okay, the second assumption is one dimensional, which means velocity profile is uniform. Uniform velocity profile. Velocity profile will remain same everywhere. So if it is an uniform velocity profile, we already know this, I already given you. What will happen to this equation? Instead of integration, I can write it as summation. Summation of what? Summation over the control surface rho v vector. This will not be dA, I'm sorry. This will be v vector dot a vector is equal to 0. Am I right? Now, if the flow, if I take a control volume, for outflow I need to take it as positive, for the inflow I need to take it as negative. I already given to you. So further modification, how can I write this? Simply, I can write it for outflow positive, right? So plus rho naught, v naught, a naught. Outflow. Okay, so this is outflow velocity, this is outflow area, this is outflow density, which will be equal to, sorry, not equal to, plus, right? So minus rho I Vi Ai. What is this rho I Vi Ai? Density at the inlet, velocity at the inlet, area at the inlet. And why I'm using minus? Because we know that inflow has to be taken as negative, outflow has to be taken as positive. That will be equal to 0, which implies rho O, VO AO is equal to rho I Vi. I'm sorry, this is space is constrained, so I'm writing it like this. And what is that equation? Continuity equation for one-dimensional steady flow. I already did the same, I already got the same equation by using some other method. But we can get the same equation by using Reynolds Transport Theorem also. So ultimately, the equations, this equation is also conservation of mass equation only. This equation is also conservation of mass equation only. This equation is also conservation of mass equation only. But we are implementing the assumption. For this equation, there is no assumption. Now for this equation, there is an assumption steady state. Now for this equation, we are adding one more assumption that it is one dimension, that is velocity profile is uniform. So for this equation, two assumptions are there, which is steady and one dimensional. I already given you when I discussing kinematics, right? I already given that when I am discussing continuity equation. So we can get continuity equation also directly by using conservation of mass of RTT. So next I am going to start with conservation of linear momentum. Okay. So linear momentum in the sense I am going to take my B as m into V vector. Okay, so this is generally linear momentum as we know already. So what will be small b is going to be mv vector by m, which is equal to V vector only. Now before going into this Reynolds Transport Theorem, what is Newton's second law of motion? Simple Newton's second law of motion. The summation of forces is equal to rate of change of linear momentum, and that is applicable for a particle or for a system only. There is a group of particle or for a particular system only. So Newton's second law of motion says for a system or for a particle, I can say that summation of forces is equal to rate of change of its momentum. Okay, I hope that you know this. Now in place of B, let me substitute mv. So what happens? B into mv vector by dt, which is equal to dou by dou t triple integration or control volume integration. This B is V vector, right? V vector into rho into dv plus surface integration, control surface. This B is V vector, okay? So V vector rho into V dot dA vector. Now listen carefully. Rate of change of linear momentum is nothing but summation of forces. So simply this equation I can write it as, instead of rate of change of linear momentum, see, don't get confused with this capital D and small d. Capital D is material derivative. Now why I am using that material derivative? Because this B can be a function of x, can be function of y, can be function of time also. It can be multiple function. So in those cases we will use material derivative. I already explained to you, but the indication here is still rate of change of the linear momentum only. So this rate of change of linear momentum is summation of f, which is equal to, I'm just substituting in place of this, I'm substituting this. Okay, now right hand side. So that's going to be dou by dou t control volume integration V vector rho dv plus control surface V vector rho, it's not dot product, it's multiplication. So this is V vector dot a. Okay, so this is dot product. Okay, this is dot product. Okay, so this equation is called as momentum equation, or in a simple or another term it is linear momentum equation. Why it is linear momentum equation? Because I am finding it for linear momentum. Next I will be doing angular momentum. Okay, now there is one more modification or one more extension which I can give. How? If I want to find out summation of forces in x direction, okay, so if I consider, let me divide it here. Okay, so for forces in x direction, And before going into that, I need to add one more point here. This summation of force includes both body forces and also surface forces. And what is meant by this body forces and surface forces? First of all, body forces means the forces which is due to some field, for example gravitational field. Okay, so due to that gravity weight of the body, right? So that is a body force, or due to magnetic field. But majorly in our studies, which we are going to stick with fluid mechanics, we will be mostly dealing with gravity force, that is nothing but weight. Okay, so body force means most of the times is going to be weight only. Now surface forces are two different forces are there. One is due to the pressure, okay, normal forces. The another one is due to shear, which is due to viscosity. Okay, so once we enter into Navier-Stokes equation, I will be using these forces, body forces and surface forces, and I will be forming equations of motion in a differential form. So actually, if you note it properly, all the equations which I am getting here, okay, this is also an equation of motion, right? Linear momentum equation, it's an equation of motion, summation of f is equal to something. But still I am getting it in an integral form. A Navier-Stokes equation will give in differential form. We will see that anyways in the next, after a few videos. Okay, now what I was saying. So this force includes both body forces and surface forces. Surface forces are pressure force and pressure force and shear stress. And body forces are weight. Majorly it is due to weight. Okay. Now if I consider all the body forces and surface forces which is acting in x direction, then I can rewrite this equation. How? Take all the components of velocity in x direction only. We know that v vector is equal to ui cap plus vj cap plus wk cap, right? So if I am taking x direction, this velocity, this is not a dot product, it's not a dot product, it's a multiplication only. This velocity has to be replaced with scalar form of it. Scalar form of it in the x direction. The x direction's velocity is u, because I am taking summation of f of x. Okay, so what will happen? Dou by dou t, volume integral. Instead of v, I will use u. Okay. Instead of v vector, I am using u. This is going to become rho dv. Very good. Plus control surface. Again, this is v vector, right? I hope that you understood this. This is v vector. So again I need to replace it with u. So u and u into rho. Okay, but this will remain still same because see, it's a dot product. Dot product means vector product. So I can do the product of two vectors. So v has to be vector and d has to be vector. So dot product will give me a scalar. So this is v vector dot dA vector. Okay. Similarly, I can write it for summation of fy, summation of fz also. I am not writing it. What will happen? In place of u, you replace it with v. In place of u, you replace it with small v. Okay, that is for summation of fy. You can write it, I hope so. And summation of fz will be equal to what? In place of u, you replace it with w. In place of u, you replace it with w. That's it. Okay, that v vector dot dA vector will remain same in all three equations. Okay. Now before concluding, I just need to give you one more point. This is summation of forces, fine. And what actually this term is indicating? This term is indicating the time rate of change of linear momentum. If you multiply this, you will be getting a linear momentum. How? Rho into dv is what? Mass. Mass of a small volume multiplied by v vector, and I am finding volume integration. So it is giving me, this total is giving me linear momentum. And similarly, this is what? That is giving me time, net outflow or net effluxes of the linear momentum, okay, over the control surface. So again, it is linking summation of forces, that is our law which is applicable for system, with control volume and control surface. So next is conservation of angular momentum. Okay, so again from the basics we know that angular momentum will be represented with m into r vector cross v vector, where r vector is the position vector and v vector is the velocity vector. So if I want to find out what is that? If I want to find out an equation for control volume and control system by using RTT, first you need to know basics. Okay, basics of this. Okay, so first of all we know this B. Now if I substitute small b, okay, what will be my small b? Capital B by m. So this m will get cancelled, so it becomes r vector cross b vector. So now wherever capital B is there, you substitute this, and wherever small b is there, you substitute this. So what will be my equation? D in place of capital B, it's going to be m into r vector cross v vector by dt, and this is for system, okay, and that's going to be equal to in place of small b, I'm substituting r vector cross v, so it becomes control volume r vector cross v vector into rho into dv, plus again in place of b I can substitute, this is for control surface, so again in place of b I can substitute r vector cross v vector into rho into v vector dot dA vector. Okay, so this is my angular momentum equation. Further I can simplify this. Rate of change of angular momentum is what? Again, this is from Euler's law, okay, which you would have studied in engineering mechanics, okay, or the basic physics in your intermediate first year or intermediate second year, 11th standard or 12th standard. So rate of change of angular momentum is nothing but torque. Okay, so in this case we will be finding out summation of torque. So this can be replaced with, either you can write summation of torque or summation of moment, whatever. Okay, let me write it as summation of moment. Yeah. So there in linear momentum, rate of change of linear momentum is nothing but force, right? Similarly, rate of change of angular momentum is torque, or in other sense moment. Okay, in whatever way you want to write, you can. Okay, torque and moment are same only, right? They are not different. Torque means the special type of moment, that's it. Okay, so this is this equation is angular momentum equation, which we are getting from Reynolds Transport Theorem, and this equation links between, this is something which we are getting from a system. Okay, so this formula moment or torque is equal to rate of change of angular momentum is for a system or a particle, and I am relating with control volume and control surface. So the last equation which I have which is going to link systems equation with control volume equation by using Reynolds Transport Theorem is conservation of energy equation, or in other sense it's a general energy equation for a control volume. So how to do this? Simple. First we need to recollect some basic concept from our thermodynamics. Okay, the first law of thermodynamics. What actually our first law of thermodynamics says? If there is a system, okay, and if suppose there was some heat transfer which is happening and some work transfer, let me write it in a differential form, some work transfer is happening, then according to first law of thermodynamics I can say that this heat transfer will get converted into, some part of this heat transfer will get converted into work, and some will get converted into its internal energy, or simply it is energy, because energy constitutes of different components such as internal energy, kinetic energy, potential energy. We already discussed about this in our thermodynamics videos itself. So generally we will keep it as internal energy, generally we will keep it as energy. That energy has different components, like internal energy, it's due to intermolecular activities, kinetic energy, potential energy, okay, and if it is entering the control volume, there will be flow energy or flow work also. Okay, so first of all we will just we will concentrate on the system. So if I am concentrating only on the system, then it's internal, then it is what is that? It's internal energy, it is kinetic energy and potential energy. So overall, by using first law of thermodynamics, I can write that this heat transfer will be equal to work transfer plus some differential energy. If I want to write it in a normal form, I can write it like during a process 1 to 2, work transfer during a process 1 to 2 plus change in the energy. Delta E implies E2 minus E1, okay. But here let us keep with the differential form itself, and this differential form, if I want to use the rate per unit time, okay, then how it will look? It will look something like delta Q by delta T, which is equal to delta W by delta T. Here it will be dE by dt, and we know that this equation is for a system only. We are defining it for a system or or a closed system to be precise. So dE by dt will be equal to delta Q by delta T minus delta W by delta T. Okay, so just keep this equation in mind, and this equation is applicable for what? It's applicable for system. Now what is our property here? The property B is energy, which is E. Okay, then what will be my small b, which is going to be E by m? Let us take it as small e. Okay, so capital energy per unit mass, that is specific energy, I am going to take it as small e. Okay, now in place of wherever B is there, replace it with E. Okay, that E is nothing but energy, and wherever small b is there, replace it with small e, which is nothing but capital E per unit mass. So do that, what will happen? Let us check. If I do that, D in place of B, it will be E, right? This is for a system, that will be equal to dou by dou T triple integral, that is control volume integral. Small b is replaced with small e. Rho, this is E, I'm sorry, this is E. Rho and E look similar. Okay, this is rho and that is E. It's dV plus again surface integral. It's E into rho V vector into dA. Okay, and this dE by dt of a system can be replaced with delta Q by delta T minus delta W by delta E. Am I right? So it's very simple, right? I can just replace this. Let me do it here, but try to do it in the next step separately. So in place of dE by dt, I am replacing it with delta Q by delta T minus delta W by delta T. So this gives us the energy equation, and this you can call it as either conservation of energy equation for a control volume, or in another word it is general energy equation for control volume. Okay, I am linking the concept of system with control volume and control surface. Okay.